Hi everyone. Today I'll be presenting my work titled Issues with Measuring Task Complexity via Random Policies in Robotic Tasks. Imagine introducing a new algorithm and evaluating it specifically over either a set of trivial tasks or overly difficult tasks. Then you will not properly characterize the capabilities of the algorithm. Or imagine an agent trying to learn the hardest task without being able to master easier task leading up to the hardest one. Then the agent will struggle to solve the hard task. These scenarios underscore how task complexity is critical in both creating benchmarks and facilitating curriculum learning. Yet, it is still an open problem on how to capture task complexity in deep reinforcement learning, specifically in a principled and computationally tractable manner. There have been numerous proposed task complexity metrics, but there is no principal validation framework that systematically assesses them. We argue that such a framework needs to have one, controlled task families with known structural variation, and two, principled a priori ordering over difficulty to guide expected results. This will ensure a comprehensive evaluation of whether such metrics can reliably capture task complexity. So, objectives are to introduce such a framework, use it to evaluate current state of the art task complexity metrics, and present shortcomings in these metrics before providing recommendations for improving them. We introduce a family of robotic reaching tasks based on two robotic arm configurations, a one-link arm and a two-link arm. The reason is that they are non-trivial but solvable and have theoretical ordering over difficulty based on control theory. This is observed by structurally varying one link length since the end effector errors scale with it. Thus, increasing link length amplifies kinematic sensitivity, which makes controlling the arm hard. Increasing degrees of freedom increases demand for joint coordination, which complicates the task. Aiding obstacles also increases demand for joint coordination. And increasing the reward sparsity makes it challenging for an RL agent to learn rewarding actions. We validate our task framework by training a state-of-the-art RL algorithm called soft data critique using a one link arm of length of 1 meter, another of length of 1.65 meter, and a two link arm with total link length identical to the former. This is a return versus step plot with step in log scale. Under density rewards, we observe that the short one link arm converges faster and at a slightly higher return, followed by the long one link arm and the two link arm. This is consistent with control theoretic expectations. Furthermore, moving from the dense to the sparse rewards, we notice that the arms take longer to converge, and in the case of the two link arm, soft actor critique was augmented with hindsight experience replay to solve the task. This shows that the reward sparsity does indeed increase task complexity, which matches our expectations. With the framework validated, we can now evaluate task complexity metrics. The state-of-the-art metrics in deep RL are based on random weight guessing. This process assumes the policy is a neural network model. It initializes the policy with random weights and deploys it untrained to collect its return samples. These are then used to compute the policy information capacity, PIC, which is the mutual information between returns and random policy parameters. High PIC values denote strong dependence of returns on policy parameters, which suggests that the policy has greater influence on performance and thus the task is easier. Also, there is policy optimal information capacity, POIC, which is the mutual information between policy parameters and optimal variability and optimality variable O. O is equals to 1 when the policy acts optimal throughout the entire episode, otherwise it is 0. High POIC values indicate that finding optimal actions is relatively easy, and thus the task is easier. These metrics are negatively correlated with task complexity, meaning that when they have high values, task complexity is low, and when they have lower values, task complexity is high. We show that we show the results of this matrix in this ordered table over difficulty as per our expectations. We immediately notice with PIC that the order is not consistent with expectations because it shows that a short one link arm task is harder than both the long one link arm and two link arm tasks. Also, POIC swaps the difficult order between the one link arm tasks. Between dense and sparse rewards, POIC states that the two link arm task with dense rewards is harder than with sparse rewards. This is not consistent with expectations, and it shows that this matrix can be unreliable. Note that all these misorderings are found to be statistically significant. The inconsistencies of this matrix could be due to RWG being ineffective in tasks with sparse solution regions in the parameter space. So to mitigate this, we suggest one, reducing the set space for solutions by introducing task inductive biases, such as dynamic movement primitives or skills, for example. We also suggest augmenting RWG with exploration strategies to help it expand into viable solution regions. Note that these improvements will definitely introduce the additional representational and search advantages that should be controlled for, normalized or explicitly acknowledged when interpreting the resulting complexity estimates. Key takeaways are that task complexity in deep reinforcement learning is critical, yet measuring it remains an open problem. New task complexity metrics must be evaluated using task families with control structural variation and ordering over difficulty, just like our framework, and that PIC and POIC can fail to reliably capture task complexity. Thank you, everybody. Look forward to your questions.